Imagine a world where time no longer ticks by the familiar rhythm of our planet's spin, or the hyper-precise hum of atoms in a laboratory. Instead, picture something far more primal, more profound, a lone planet, drifting through the endless dark, untethered from any star, its motion so constant and pure that it has become the new heartbeat of the cosmos. This isn't science fiction. This is the reality of a rogue planet scientists have harnessed to redefine time itself. For centuries, humanity has looked to the skies for answers, but never before have we found a clockwork so elegant, so perfectly isolated, that it challenges our very understanding of what time means. This celestial wanderer, known as Kronos 9, moves with a silent, relentless grace through the void, a cosmic orphan on a journey that began billions of years ago. Its story is one of mystery and marvel, a planet born among stars, then cast adrift, now serving as a natural timekeeper far beyond anything humans have ever engineered. As we trace its path across the galaxy, we unlock secrets not just about the universe's past, but about how we might navigate its future. This is more than an astronomical curiosity. It is a revolution in the making, one that could synchronize spacecraft, refine physics, and even shift our philosophical gaze from earthly confines to the grand, universal flow of existence. Today, we embark on a journey to uncover how this rogue planet became a new benchmark for time measurement. We will explore its startling discovery in the deep reaches of space, the cutting-edge technology that allows us to track its every move, and the breathtaking implications this holds for science, society, and our place in the cosmos. From the origins of Kronos 9 to the collaborative efforts of astronomers and engineers worldwide, this is a tale of human ingenuity meeting cosmic wonder. So settle in, open your mind, and prepare to see time in a light you never thought possible, where the boundaries between the infinite and the intimate beautifully blur. It was a flicker in the data, a ghost signal in the vast ocean of noise that washes over our telescopes every night. Deep within the Orion Arm, a star seemed to brighten for no apparent reason. Then, just as mysteriously, it faded back to its normal state. To most, it would have been a blip, an anomaly to be filed away, but to a team of astronomers sifting through sky survey data, it was a siren's call. They had just witnessed the signature of a gravitational lens, a phenomenon predicted by Einstein where a massive object's gravity acts like a magnifying glass, warping and amplifying the light from a star far behind it. But there was a problem. The math was all wrong for a star or a black hole. The mass was too small, the event too clean. The only thing that fit the model was a planet-sized object, and it was moving fast, utterly alone in the dark. They had found a rogue. This cosmic drifter was soon designated Kronos 9, a name befitting its future role. Confirming its status was a painstaking process of elimination. For months, astronomers pointed every available instrument at that patch of sky, searching for any hint of a host star. They found nothing. No infrared glow, no gravitational wobble, no evidence of a solar system. Kronos 9 was truly solitary, a world orphaned from its birthplace and set adrift on an eternal journey through the galaxy. Its isolation is its greatest gift to science. Unlike planets bound to stars, which are constantly tugged and jostled by gravitational interactions, Kronos 9 sails through the relatively calm interstellar medium. Its motion is breathtakingly constant, a straight line trajectory through space that is almost entirely free from the perturbations that complicate life within a solar system. This pristine quality is what caught the attention of experts like Dr. Elena Vance from the International Astronomical Union. She describes Kronos 9 not just as a planet, but as a time capsule from the early universe. When it formed billions of years ago, it was likely ejected from its infant solar system in a violent gravitational dance with sibling giants. That means its composition, its speed, its very essence is a frozen record of conditions from a time when our galaxy was young. It carries pristine clues about how planets are built and the chaotic dynamics that shape galactic evolution, but its most immediate value lies in its motion. That unwavering, predictable path makes it a perfect candidate for a new kind of clock. It is a natural metronome ticking not in seconds, but in the steady, relentless progress of a world in motion. This discovery did more than just add a new object to a catalogue. It opened an entirely new chapter in astronomy, forcing us to look beyond our terrestrial and solar-based concepts and reconsider how we measure time itself on a truly cosmic scale. To understand why Kronos 9 is such a revolutionary timepiece, we must first appreciate the profound stillness it experiences. Adrift in the emptiness between stars, it is free from the gravitational chatter that fills a typical solar system. There are no planetary neighbors to nudge it slightly off course, no bloated parent star exerting tidal forces that could minutely alter its speed. This isolation grants it a state of near-perpetual, unaltered motion. It is the ultimate embodiment of Newton's first law, an object in motion staying in motion, with nothing significant to stop it or change its path. Its velocity is not just constant, it is pristine. This quality transforms its journey into a natural temporal standard. Think of it like this. For centuries, humanity used the steady, predictable swing of a pendulum to mark the passage of seconds. Later, we advanced to atomic clocks, which count the unwavering vibrations of cesium atoms. Kronos 9 operates on the very same principle of reliable, repetitive motion, but on an astronomical scale. Its steady drift through the void is the swing of the pendulum. Its unchanging velocity is the vibration of the atom, but its scale makes it far more stable over the long term. As theoretical physicist Dr. Marcus Thorne so eloquently puts it, these rogue worlds act as cosmic metronomes. Their motion provides a stable reference frame that is completely independent of the complicated, ever-changing dynamics within our own solar system. But a clock is useless if you cannot read it. So how do scientists actually tell time by watching this distant world? The key is to measure its position against the most fixed background we can find. While the stars in our sky appear stationary to the naked eye, they are all moving, swirling along with the rotation of our galaxy. To find a truly unmoving reference, astronomers look far beyond our Milky Way to quasars. These are the intensely bright cores of distant galaxies, powered by supermassive black holes. They are so incredibly far away that their apparent motion in the sky is negligible, effectively making them fixed points in the cosmos, like permanent celestial lighthouse beacons. By training an array of powerful radio telescopes on Kronos 9 and precisely measuring its position relative to these quasar guideposts, researchers can detect unimaginably tiny shifts in its path. We are talking about movements on the scale of nanometers across distances of light years. By tracking these minute changes over years and decades, they can derive an exquisitely precise time interval. Each measurement is a tick of this galactic clock. This method boasts a huge advantage over our most advanced atomic clocks here on Earth. Those terrestrial marvels, while incredibly precise, can be influenced by local environmental factors. Changes in gravity, magnetic fields, or even temperature can cause tiny drifts that require constant correction. A rogue planet's motion, however, is buffered by the immense emptiness of space, making it a potentially more reliable and stable long-term standard. The implications of this reach far beyond simply keeping better time. This celestial clockwork could revolutionize deep space navigation. Future probes traveling to other star systems could use the predicted positions of rogue planets as a universal GPS, triangulating their location in the void without needing constant contact with Earth. Perhaps even more exciting is its potential for testing the very fabric of physics itself. Einstein's theory of general relativity describes how gravity warps space and time. By observing the flawless motion of Kronos 9 over centuries, scientists could look for any minuscule deviations, any whispers in the data that might hint at new physics or refinements to our understanding of the universe's fundamental laws. This lonely world is not just a timekeeper, it is a laboratory for probing the deepest mysteries of existence. So what makes Kronos 9 the ideal candidate for this incredible responsibility? It is not just any rogue planet, it is a paragon of stability, hurtling through the Orion arm of our galaxy at a steady 50 kilometers per second. Its velocity is so unwavering that it makes the most precise man-made machines seem erratic by comparison. This constancy stems from its profound isolation. Unlike planets bound to stars, Kronos 9 feels no gravitational tides from a sun, no periodic tugs from sister planets, and negligible influence from the sparse dust and gas of interstellar space. Its path is clean, its motion pure, a solitary traveler on a highway of near-perfect emptiness. This provides a consistent baseline for measurement that is utterly unaffected by the chaotic gravitational chatter that constantly perturbs objects within solar systems. Monitoring this cosmic waypoint requires a global effort and technology operating at the very edge of possibility. An armada of observatories keeps a constant watch. Space-based telescopes like the James Webb peer at it in infrared, while down on Earth, vast radio telescope arrays such as the Very Long Baseline Interferometry Network combine their signals to create a virtual telescope nearly the size of our planet. This coordinated gaze allows scientists to pinpoint the planet's location with almost unbelievable nanometer precision across light years of distance. They are not just watching it move, they are measuring its journey atom by atom across the sky. The data collected is so vast and complex that it requires supercomputers to unravel. Every minute shift in its position is recorded, analyzed, and compared against the fixed backdrop of distant quasars. This is where the timekeeping magic happens. For example, as Kronos 9 transits across a predefined grid of these celestial markers, its passage marks time intervals with a staggering accuracy that surpasses our best atomic clocks by a factor of 10. A single clean pass can provide a more reliable timestamp than a century of meticulously maintained atomic time. This is not just an incremental improvement, it is a leap into a new era of precision. The success of this case study is a triumph of international collaboration. Astronomers from observatories on every continent share data and telescope time, working in unison to track this faint dot of light. Their collective effort transforms Kronos 9 from a distant curiosity into the foundation of a new temporal standard. But the ambition does not stop with one planet. The ultimate goal is to find others like it. Imagine a future where we have a network of these cosmic clocks, a constellation of rogue planets scattered across the galaxy, all serving as independent timekeepers. By cross-referencing their motions, we could create a timekeeping system of unimaginable robustness and longevity, a legacy that could outlast human civilization itself. Kronos 9 is the proof of concept, the first tick of a clock that could one day measure the age of the universe itself. Capturing the faint whisper of a planet light years away with no star to illuminate it is a monumental technical challenge. It pushes the very edge of what is possible in observational science. The key lies not in a single revolutionary instrument, but in a symphony of technologies working in perfect concert. At the heart of this effort are the great eyes on the sky, both in space and on the ground. The James Webb Space Telescope, positioned far beyond Earth's distorting atmosphere, acts as a primary sentinel. Its infrared vision is perfectly suited to detect the feeble heat signature of Kronos 9, a cold world glowing dimly with the residual energy from its formation billions of years ago. But even Webb's immense mirror is not enough on its own. To achieve the nanometer-level precision required, astronomers combine its data with observations from a completely different kind of system, the Very Long Baseline Interferometry Network. This is not a single telescope but a coordinated array of radio dishes scattered across the globe. By synchronizing their observations using atomic clocks, these separate facilities can act as one colossal virtual telescope with a diameter equal to the entire planet. This technique allows scientists to pinpoint the position of Kronos 9 with staggering accuracy, effectively measuring its slow drift against the fixed backdrop of the universe. Yet, the raw data from these telescopes is just the beginning of the story. The information they collect is not a simple picture but a flood of complex signals, a digital ocean of light curves and radio waves that must be deciphered. This is where computational power takes center stage. Supercomputers process petabytes of this data, running sophisticated algorithms that filter out noise from cosmic rays, interstellar dust, and atmospheric interference. The goal is to isolate the pure, clean signal of the planet's motion. Innovators like Dr. Lin Nguyen, a lead engineer at the Time and Frequency Division, emphasize that this is a constant battle against uncertainty. We are pushing the limits of sensitivity and computational power to turn celestial motion into a usable time standard, she explains. Every calculation is a step toward transforming an abstract astronomical observation into a practical, ticking clock. The pursuit of greater precision has also spurred remarkable secondary innovations. Quantum-enhanced sensors are now being integrated into these networks. These devices exploit the strange laws of quantum mechanics to reduce measurement noise to almost nothing, allowing for even finer detection of the planet's minute positional shifts. Furthermore, artificial intelligence plays a crucial role in forecasting. AI-driven models, trained on decades of positional data, can now predict the path of Kronos 9 centuries into the future with incredible confidence. These models account for the minuscule gravitational influences of distant stars and the tidal forces of the galaxy itself, ensuring our cosmic clock remains accurate for generations to come. This technological symphony does more than just track a wandering planet. The advances developed for this project have ripple effects across countless other fields. The same quantum sensors are revolutionizing medical imaging. The data processing algorithms are improving global telecommunications networks. The AI predictive models are helping us understand climate change on Earth with greater clarity. The quest to build a clock from a starless world is in itself a powerful engine of discovery, proving that by looking outward to the cosmos, we often find new ways to improve life right here at home. The synergy between the immense hardware in space and the intelligent software on the ground is what makes this entire endeavor possible, ensuring that data traveling across light years of emptiness arrives at our laboratories with flawless integrity. But how does this incredible cosmic clock stack up against the way we measure time today? For generations, our most precise time standard has been the atomic clock. These remarkable machines rely on the incredibly steady vibration of atoms like cesium to mark the passing of a second with near perfection. They are the heartbeat of our modern world, governing everything from financial markets to the GPS that guides us. Yet, even these technological marvels have their weaknesses. They exist within Earth's gravity and are subject to tiny environmental influences, from fluctuations in temperature to magnetic fields. This means the most advanced atomic clocks on Earth require constant, meticulous calibration to remain in sync with each other, a process that, while highly effective, introduces a microscopic level of human-maintained error over very long periods. Then there is solar time, the ancient rhythm of our planet's rotation. This is the original clock, the cycle of day and night that has dictated human activity for millennia. But Earth is not a perfect spinner. Its rotation is gradually slowing down due to the gravitational tug of the Moon, and it can speed up or slow down minutely due to events as massive as earthquakes or even the shifting of ocean currents. These planetary wobbles mean that a day is not a fixed, immutable unit. We have to add leap seconds every few years to our official clocks to keep them aligned with the solar day, a clunky fix for a fundamental instability. Now consider Kronos 9. This rogue planet, adrift in the void, operates on a completely different set of rules. Its motion is not a rapid atomic vibration, but a slow, majestic, macroscopic glide through interstellar space. Completely free from the gravitational embrace of any star, its velocity is astonishingly constant. Where an ensemble of the world's best atomic clocks might show a nanosecond of collective drift over a year, Kronos 9's trajectory has shown no measurable deviation at all over the same time frame. It is a pendulum swinging in a perfect vacuum, utterly undisturbed. This gravity-independent nature makes it an ideal candidate for a universal time standard, one that could synchronize future deep space missions with a reliability we can only dream of with Earth-bound systems. Of course, this new paradigm is not without its own profound challenges. The very thing that makes Kronos 9 so stable, its immense distance, is also its greatest obstacle. The signals we use to track it, traveling at the speed of light, take years to reach us. This introduces a significant delay between the event, the planet's movement, and our observation of it. We are always looking at where Kronos 9 was, not where it is. Compensating for this light time delay requires incredibly complex calculations, building a model of its past to predict its present. Furthermore, adopting such a standard would be a monumental feat of international cooperation. It would require a global consensus to redefine the second not by the atom, but by the motion of a distant world, entrusting our most precise measurements to a celestial body we can never directly visit. This leads us to a fascinating crossroads. Could rogue planet time ever truly replace atomic time here on Earth? The practical hurdles are immense, suggesting that for daily life and most technologies, our current atomic clocks will remain the convenient and sufficiently accurate choice. But for the grandest of human ambitions, like establishing a permanent presence on Mars or sending probes to other stars, a cosmic clock like Kronos 9 offers a tantalizing solution. It provides a fixed point of reference outside our own solar system, a universal metronome against which all local times can be synchronized. The real future may not be about replacement, but about integration, creating a layered timekeeping system where atomic clocks handle our earthly needs and rogue planet time guides our journey into the cosmos, perfectly balancing the relentless drive of innovation with the practical realities of life on Earth. This shift toward a cosmic clock does far more than just improve our instruments. it fundamentally rewires our approach to understanding the universe itself. For scientists, a time standard anchored to a rogue planet like Kronos 9 is not merely a tool, it is a key to unlocking some of physics' greatest mysteries. Imagine testing Einstein's theory of general relativity with a precision never before possible. Tiny discrepancies in how gravity warps space-time could be measured across interstellar distances, using the planet's unwavering motion as a reference. Cosmological models, which try to chart the history and fate of the entire universe, often rely on precise timing of cosmic events like supernova or gravitational waves. A universal clock, free from our solar system's local quirks, would provide a pristine backdrop against which to compare these events, potentially revealing new physics hiding in the margins of our current equations. The practical benefits for society are equally transformative, extending far beyond the realm of pure science. Consider navigation. Our current GPS systems are a marvel of engineering, but their incredible accuracy is entirely dependent on the precise timekeeping of atomic clocks onboard the satellites. Even a microsecond of error can translate to a positioning mistake of hundreds of meters. A more stable, universal time standard, beamed from deep space observatories, could act as an ultimate calibrator for these networks, making them exponentially more reliable and secure. This would revolutionize not just driving directions, but the entire global infrastructure that relies on precise timing, from air traffic control to financial trading networks where transactions are timed to the millionth of a second. But the most profound application lies in our future as a spacefaring species. As we set our sights on establishing bases on the Moon and Mars, and eventually sending probes beyond our solar system, we face a colossal coordination problem. How do you synchronize missions between planets that have different day lengths and are separated by vast distances where communication delays are measured in minutes or hours? A time standard based on Kronos 9 offers an elegant solution, a shared cosmic pulse that every spacecraft and colony can set their clocks to, regardless of their location. It becomes the heartbeat for an interplanetary internet, ensuring that a data packet sent from a research station on Mars arrives at a telescope orbiting Jupiter at exactly the right moment, enabling a new era of seamless deep space communication and cooperation. This technological leap inevitably pushes us into deeper, more philosophical territory. For all of human history, our conception of time has been intrinsically local, tied to the sun rising and setting outside our window. We built our clocks in our own image based on the rhythms of our world. Adopting a time standard from a lonely wanderer in the dark challenges that Earth-centric perspective. It forces us to think on a galactic scale, to see time not as a human invention but as a fundamental property of the cosmos, a rhythm we are simply tuning into. Futurists suggest this could inspire a new humility and a broader sense of place in the universe, much as the first images of Earth from space fostered a sense of global citizenship. However, this bright future is not without its complex challenges, questions that move from the technical to the deeply ethical. If we are to have a universal time, who gets to define it? Who governs Kronos time? This is not a matter for astronomers alone. It would require an unprecedented level of global diplomacy, likely necessitating a new international body under the umbrella of the United Nations to oversee its use and maintenance. The goal would be to prevent any single nation or corporation from controlling humanity's master clock, ensuring this resource remains a commons for all people. Furthermore, we must address equitable access. The advanced technology required to receive and utilize this time signal is immense. How do we ensure that developing nations and emerging space programs are not left behind in this new temporal era, creating a new kind of cosmic divide? The journey of Kronos 9 asks us to look upward with wonder, but also inward to consider what kind of future we want to build together in the vast expanse of space and time. From a solitary speck first glimpsed through the gravitational lensing of a distant star, to a cornerstone of how we may one day mark the passage of moments across the cosmos, the journey of Kronos 9 is nothing short of revolutionary. This rogue planet has gifted us a perspective shift, challenging the very foundations of our Earth-centric clocks and offering a timepiece forged in the silent, stable depths of interstellar space. We have traveled through the science of its discovery, marveled at the technology that tracks its unwavering path, and pondered the profound implications of a universal clock that belongs not to one world, but to the galaxy itself. This story is a powerful reminder that the universe is constantly presenting us with new tools for understanding, if only we have the curiosity and ingenuity to recognize them. The mysteries of the cosmos are infinite, and Kronos 9 is a brilliant key, unlocking one door only to reveal a hallway lined with countless others, each promising a new revelation about the nature of reality. Consider how this cosmic clock might change your own view of time, from a local rhythm to a universal constant. We would love to hear your thoughts on this incredible journey in the comments below. If you found this exploration into the frontiers of time and space fascinating, please subscribe for more content that unravels the wonders of the universe. Join us next time as we venture into another captivating space mystery.